Good morning. Here we are yet again for another lovely session of CENG 3325 Structural Analysis. So today we're going to be finishing up on trusses, and we're going to be looking at a final topic of truss theory, or really truss methods, I should say, not truss theory, and that is the method of sections. Trusses, the method of sections. So let us discuss the theoretical principle behind this first. The principle of the method of trusses is really quite simple, but implementing it can be difficult depending. Actually, I believe that should be EL or LE, maybe. Anyway, so principle, the theoretical principle here is that for an object to be in equilibrium, every piece of that object must also be in equilibrium. And we have seen this already when we briefly looked at member internal forces. So in terms of what this means, let's consider this for a moment. So let's consider something like this. Maybe I'll give a brief example. Let's say I had an object, maybe a great big box. Let's say I have a great big box supported by, I don't know. Let's say it's supported by a couple large rods here. Then maybe a bar. I know this looks nothing like a truss. I'm just illustrating again the principle of method of sections. And then maybe there's a bar across. And from that, I'm hanging two cords, and then that hangs from the ceiling. Okay, so this is a fairly convoluted example, but I want to illustrate the basic idea. It looks kind of like Stonehenge or something. But anyway, so I have this big box being held up by this weird framework. But anyway, the point of this that I'm really trying to illustrate is that I can look at this as either a single object, or I can look at this as multiple objects. So if I want to look at this, entire frame and box, well, I can look at this many different ways. I could look at this as a single object, including the ropes. And at that point, I could almost treat it as a point object. I could say the applied force up here, the reaction force here, if that was force A, it would be like AY. And then maybe there'd be the combined weight here. So if I take equilibrium at this point right here, that would be just a support at point A, and then the combined weight of all of these things. And so that would be fairly straightforward. And that would be the net force on Y with the two horizontal components of the tensions canceling out. Or I could cut it somewhere else. Imagine I were to cut it somewhere midway. What if I were to cut it here? Let's say I cut it here at, let's call this B. Well, what would I have? And let's say I isolate this bottom part here. What would I see? Well, if I were to draw a free body diagram of just that object, or just the cutout portion, I should say, I would have this and the cut portion of the legs here. And then I would have two forces revealed by the cut. Now I could say that there would be, now truth be told, I could say there's moments in here, but I'll keep things simple right now by saying there's just maybe axial force in there. Keep things relatively simple. So maybe that would be N at point B, the normal force at point B, or the axial force at point B, and then the weight of box plus maybe 1/2 the legs. And I'm not being very proper with my subscripts here. I'm just trying to illustrate the basic principle right now. So the basic idea, again, is that we can cut objects. If we cut objects, so basically the big moral here, if we cut objects, we reveal internal forces that will keep the object at equilibrium. And in fact, you know what? I might call this principle 1, and I think I'm going to add a principle 2 to this as well. On the next slide, I'll add a principle 2. I think that's kind of important. And I think I also want to add a principle 2 that will go along with this to make the method of sections practical. So again, this is basic statics, but it's, again, important to remember. Principle 2. In order for an object to be in equilibrium, it must be in equilibrium, or I should say maybe must be in rotational equilibrium, rotational equilibrium about any axis of rotation. Any axis of rotation. So for example here, if I were to draw out a truss, consider a basic truss here. And let's look at the external forces on here. Let's say there is, okay, let's say these are joints, let me label the joints first. Let's say these are joints A, B, C, and D, E, F, G, and H. And then let's show the external forces on here. Let's say there is a force of, I don't know, 10 kips here, maybe 15 kips here, just some random forces. And let's say this is simply supported, so there's a dy here, and a dx here, and maybe a hy here. Okay, so fairly straightforward truss. So if I wanted to look at equilibrium, I could sum equilibrium of this truss about any point, and it still should come true, or still should be true. So if I look at a sum of moments about point A, that should equal 0. If I do a sum of moments about point F, that should be 0. If I do a sum of moments about H, that should be 0. Doesn't matter where we sum moments, all of this should come to 0. And interestingly enough, that point doesn't even have to be on the object. I can have a point way out here, I don't know, that I'd call point Z or something. I don't want to do a cardinal axis. Let's have some fun. Let's make it point Q for an oddball. So sum of moments about Q, that also has to equal 0. So again, if an object is to be in equilibrium, if a 2D object is in equilibrium, you can sum moments about any point in the plane. About any point in the plane.
I have a question.
Yes.
You talked about how important it is to have your especially rotationally, but what's a real world example where an object would be rotating?
Oh, okay. So the question is, how important is it to have a rotational equilibrium in the real world? Is that kind of, or is there an example of an object that's not in rotational equilibrium?
Yeah, because there are some pretty simple ones where, yeah, if you put enough weight on it, it will bend, it will deform, but will it rotate?
But okay, that's another question. Okay, that's actually interesting. Bending is rotation. Bending fundamentally is rotation. Now, if you're talking, now usually when we say it's in equilibrium, we're talking about things where deformation is small, and so it's not having massive rotations. So if this thing was not in rotational equilibrium, well, imagine in most civil engineering applications, if something is not in rotational equilibrium, you have a problem. You have a very large problem. In other words, have a highway bridge and and blow up one of the bridge piers and watch what happens. You'll have a bridge deck that's not in equilibrium. That's an example of non-rotational equilibrium, because although it'd be tricky to think of something that, okay, I'll back up. How could I have something that, but the problem with that is that's also an example where it's not in translational equilibrium. So can I have an example of something that would be in a civil engineering application that would be in translational equilibrium but would not be in rotational equilibrium? Maybe something sort of like a floodgate or something that needs to rotate, or some sort of barrier that rotates on an axis or something like that. That might be in rotational. That would be not, as it's moving, that might be in non-equilibrium in a rotational state. But anything that's going to be fixed to the Earth, that's going to be in equilibrium. Does that make sense?
Yeah, I believe so. They usually come together, don't they?
They usually come together.
It's like if it's moving translationally, it's also.
Yes, usually if something's moving translationally, or usually if something's moving rotationally, it's also moving translationally. It's hard to have one and not the other. Pretty much the only case that I can think of would be something like, okay, if you had something rotational or translational equilibrium without rotational. Without rotational equilibrium. It would have to be something that's rotating about a fixed axis. About a fixed axis passing through the center of mass even. It's very specific. Passing through mass center. So for example, imagine you, I don't know, I don't think they actually build floodgates like this, but let's say you did. This is probably not the most efficient design. But let's say you had a great big body of water here, and you have your dam and a floodgate. I'm looking at this in plan view. I'm looking at this from above. And let's cut that out there. And let's say I have my dam here, continuing on in either direction, continuing on that way, and continuing on to the right here. And then I want some sort of floodgate or a sluice gate that I can open up. Now, this would not be the most ideal design for a gate. I don't know why you would build this, but let's say you did. You could have a gate like this, and it's going to sit in the middle there and form a tight seal, tighter than is indicated by my drawing. And I have an axis of rotation here. Or a turbine would also be a mechanical engineering application of this. But basically, a thing like this, if it's going to rotate like this, the location the three-dimensional location of its center of mass is not changing. So it has to be in translational equilibrium. But it's definitely not in rotational equilibrium because it's rotating. Or any kind of thing with a fixed axis, fixed shaft, a power plant turbine would be a great example. Something that, like a turbine in a power plant, it looks like, kind of has turbine blades like that. It's not going anywhere. It's just rotating. So it's not actually going to go anywhere. Maybe it spins like that or something, but does it spin like that? Yeah, it spins like that. So it might spin like that, but it's not going to go anywhere. Its actual center of mass is not going to move, but it is going to rotate. So I really do have to grasp at straws though to find examples of things that are in translational equilibrium but not rotational. You have to go to.
I think in San Antonio there's like a hotel or like a restaurant that like spins at the very top.
Oh, yes, rotating restaurants. I know exactly what you're talking about. At the top of the Tower of the Americas in downtown San Antonio, in the Was it the what was that built for? That was built for the Hemisphere, the famous 1960s Hemisphere. It was one of those Space Needle type things. And there's one in San Antonio, and you can go there and oh boy, that restaurant up there is expensive.
Downtown.
It's a rotating restaurant, yeah. It's not as nice. Oh yeah, yeah. The one in San Antonio, you have a great view. Yeah, we have a rotating restaurant in the thing downtown, but everyone's just saying the view's not as nice. But no, that one in San Antonio, it's you better be prepared to have a nice meal. But anyway. Although I'll tell you, when a friend of mine went there as broke college students back in the day, we wanted to go to the top of the tower, but we realized the ride up to the tourist elevator had been like $20 a person, and so we didn't want to spend that much. So instead, thankfully, we were there on a slow day when it was easy to just walk in and get a reservation. So we each rode the free elevator to the top and had the great view and everything, and each ordered one Coke. But that has nothing to do with structural mechanics. So anyway, but yes, a rotating restaurant is another great example. Although, again, that's definitely a niche application. There's not a lot of applications of a rotating restaurant. Ooh, maybe I should do that for your design project in this class. It'd be great. All the dynamic factors and the bearing design, and we could have design the electrical stuff too. It'd be so much fun. Rotating restaurants. No? Okay, fine. Where's your sense of adventure? All right, so moving along, let's see how we apply this to trusses. Trusses, the method of sections. Although one of those Space Needle type structures would be great during a zombie apocalypse. Although it's probably a little too visible, so who knows? Yeah. All right, so trusses, the method of sections. How do we do this? The basic idea is that we will cut out a section of a truss, cut out or separate a section of a truss that contains the forces or the members that we are interested in. The member forces we are interested in. So, if convenient, we may sometimes first solve for truss reaction forces, treating the whole thing as a single rigid body, as we've done before, as we did in the method of joints. We may first solve for truss reaction forces, but not necessarily. There may be cases where it's not so convenient or just not necessary. Let's see. And then, so the basic idea for the hard part of this, or the difficult part, is selecting your cut. The difficulty is in selecting the cut, or selecting the isolated section. Some guidelines. Actually, I might do this on the next slide because there's going to be a lot of guidelines. Okay. So guidelines on selecting your section. Guidelines on selecting your cut. This is a little bit tricky. Choosing your section. One, the cut line must always cross members. Directly across members. Not through joints. Things get complicated if you try to cut through a joint. And the reason that it gets complicated is because we treat joints as idealized point particles. And if you try to cut through joints, you'll have a hard time figuring out what force is on your. If, for example, if you try to cut if you have a joint which really is an idealized point particle, and you have multiple forces on here, well, and if your cut line comes along here and tries to cut it, well, which forces do you include in this section and which don't you? You might be tempted to say, oh, well, obviously I'll choose these here, but think about it. I can always move forces around along their line of action. So who's to say that that force isn't really here on that free body? And that's the problem with cutting across joints. You never want to cut across joints. We avoid joints entirely with the method of sections. 2. You'll always want to make sure your cut section includes all desired forces if possible. If possible. Sometimes it's not possible. For example, if I ask you for 5 member forces, it's not going to be possible to cover all of those with one cut. And 3, make sure to include no more than 3 cut members in your section. Wow, that's really bad. Members in your section, as each cut member equals another unknown force. Reveals another unknown force. Because remember, we're only going to have 3 equations of equilibrium. So at any time, if we cut across 3 members, if we cut across more than 3 members, then we're going to have more than 3 unknowns. And that's going to be a problem. So we have only 3 equations of equilibrium. We have sum of forces x, sum of forces y, and sum of moments. Although sometimes we can get away with summing moments multiple times, but we can never solve for more than 3 unknowns. That's fundamentally impossible. At least on a single free body diagram. All right, questions on this so far? Okay. Let's see, what else? I also want to discuss where is this good for? Applications, or when to use method of sections. Generally, if you are interested in all the forces in a member or all the forces in a truss, in every force in a truss, use method of joints. Let's say either on paper or using matrix methods. Matrix methods. Either or. Generally, 9 times out of 10, that's going to be more efficient than trudging across the truss with a method of sections approach. Usually, because the nice thing about the method of joints, it is a bit tedious, but each individual free body diagram is quicker to draw than one of your free body diagrams for the method of sections. Generally, there's some wiggle room there. But generally, if you're truly interested in every single member force, you're going to use more of a method of joints approach, which is why most structural engineering software is going to use more of a matrix approach. It's going to use more of a finite element or it's going to use more a matrix approach that's much more involved with the example I did in the previous lecture. It's going to use more energy methods and things that we'll learn later in the semester. So when do you use then? If you're not going to use it when you want every member force, when will you use method of sections?
For specific ones.
Yes, exactly. Method of sections is ideal for trusses when you're interested in a specific member force. Or a handful of member forces. Especially of member force far from a support, where you'd have to do a lot of individual method of joints in order to work your way there. Far from a support. Especially a member far from a support. So, a member far from a support, etc. So, now, of course, this does raise the question, when would you only be interested in one member force when you're designing something? If you're actually designing something, would you ever be interested in just one member force? Well, design, probably not. I would really have to stretch to find a practical application, industry application for purely the method of sections. Maybe if you were being extremely lazy and you were thinking, or you needed to replace one member on a truss or something like that, and so you're only interested in the forces in one member. But even then, as a structural engineer, I'd be very skeptical of anyone stamping off on a work order for replacing one or only analyzing a single force on a single member. But anyway, the main reason I want you to learn about this is because this method of section stuff, while it does have limited uses, practical uses in trusses, it is a good way to treat truss theory, to explore truss theory. But more importantly, when we get to our method of frames, or when we start looking at frames, we're definitely going to be looking at the method of sections. It's a primary way of solving for frame forces. So we'll be using that later on in the next lecture or two. So. And also we look at member internal forces, etc. So any questions on this theory of method of sections? Okay. So I think that about covers the theory for the method of sections. All right, any other questions? Okay. All right, I think that'll do it for now. Thank you for watching, and as always, thank you.